right. Well, it's 7:30 p.m. I'd like to call this meeting of the Warren Astronomical Society to order. This is, of course, our virtual Macomb meeting since we are not able to get into Macomb, but good to see everybody's faces on the WebEx. Got a good crowd tonight, and I'd like to thank everybody who's joining us on YouTube or simply the broadcast. A reminder that if you are on YouTube and you do have an account there, you can comment. Our program, our publications chair, Jonathan, is monitoring the comments so that they can be relayed to those of us live in the WebEx. So I'd like to give a shout out to everybody out there. Bill Beers, Dale Hollenbaugh, Dale Parton, Dale Teamy, Doug Bach, Jerry Voorhees, Glenn Wilkins, Jim Shedlowski, John Stewart, another John, Catherine, Ken Burton, Ken Lord, Michael D., Michael F. Riyad, and Steve. So great crowd tonight. And I hope everybody's doing well. I do want to add that we are among the few astronomy clubs here in Michigan that are doing these virtual meetings to keep our club active and doing astronomy during the pandemic lockdown. So this is really special. It means a lot to me to see all of you and hear from all of you. And I hope that it's keeping you all occupied. So, got a few things to cover tonight. We're going to start things off with In the News and the Sky. We do take volunteers for this, so if you are interested in doing it at an upcoming meeting, that would be great. We've got Ken Burton on deck for the May quote-unquote Macomb meeting, which probably will not be held at Macomb. But anybody else interested, we've had Dale Parton, Dale Teamy, myself, Bob Tremblay all do it in recent months. And anybody else willing to give it a try, put your own spin on the news, please do. In the meantime, I'll be taking you on a brief trip through the news tonight. So if you needed any more evidence that Einstein was onto something when he covered general relativity, we've got it. So, observations made with the ESO's Very Large Telescope have revealed for the first time that a star orbiting the supermassive black hole at the center of our Milky Way moves just as predicted by the theory of general relativity. Its orbit is shaped like a rosette or a spirograph, pictured here in an artist's rendering, and not like a simple Newtonian ellipse. This effect, known as Schwarzschild precession, had never been measured before for a star around a supermassive black hole. Now, the orbit of Mercury does something similar around the sun, but finding it for a star around a black hole is a first. So this artist's impression does illustrate the precession, exaggerated for visualization. This second simulation shows the orbits of many stars close to our supermassive black hole, Sagittarius A star. One of them is named S2. It orbits for 16 years, so it's got a very tight orbit around the black hole. And it's passing very close to the black hole, as you might imagine. So this is basically a live laboratory to test gravitational physics and specifically to test general relativity. Research into S2's orbit was presented in a paper called Detection of the Gravitational Redshift in the Orbit of Star S2 near the Galactic Center Massive Black Hole by the Gravity Collaboration, which appeared in the journal Astronomy and Astrophysics on 26 July 2018. So once again, Einstein knew what he was on about. Oh, we're doing cosmic fireworks tonight. Well, there's an astonishingly bright supernova detected back in 2016 that turns out to have a surprising origin. SN 2016 APS was found by the Pan-STARRS telescope in Hawaii, Panoramic Survey Telescope and Rapid Response System. It's so bright that it obliterates the light of its surrounding galaxy, which is an undistinguished, unnamed cluster of stars, about 4 million light years away. And it has released a record-breaking amount of radiation into space. It's the most massive supernova ever observed, between 5 to 10 times more massive than a typical supernova, and then, in turn, 50 to 100 times more massive than the sun. So, what's going on with this incredible display of cosmic fireworks? Well, it is a pulsational pair instability supernova, which was a new arrangement of words for me. Two smaller stars combined and then went supernova together, resulting in a emissions fingerprint with a very suspiciously high amount of hydrogen. Normally, if a massive star is going supernova, it's already gone through its hydrogen, its helium, and several other elements on the way to iron. This, because it was apparently two younger but very massive stars, came together and then exploded. There's a lot of hydrogen left in the debris field, which real interesting. Not many of them out there. So, very cool. Speaking of old data having interesting ramifications, tucked away in years old data from the late lamented Kepler probe is a treat. Kepler 1649c, located 300 light years from Earth, is the most Earth-like yet of Kepler's confirmed planetary finds. It is slightly larger than Earth, receives 75% of the light that the sun gives to Earth, and is located within the habitable zone of its system, meaning liquid water might exist on 1649c. There is, however, a catch with Earth 2. It's around a red dwarf star. Red dwarf stars are notoriously volatile, and that means that conditions might be, as NASA admitted, challenging for life. In the meantime, here's an artist's rendering on what you might see if you were standing on its surface. As far as I'm concerned, yeah, okay, we're calling it a second Earth, but it could easily be a second Venus. We don't yet know its atmospheric composition either. First interstellar object to visit our solar system that we are aware of, that we confirmed, Oumuamua, has a puzzling shape. Unlike its successor, I-2 Borisov, which appears to be a more familiar icy comet, Oumuamua had a dry appearance and an elongated profile, leading to speculation it was shaped like a cigar or maybe a pancake, tumbling through space. A new study published on April 13th in Nature Astronomy offers a first comprehensive answer to these questions. The study used computer simulations to show that objects like Oumuamua, here depicted as cigar-shaped, can form under the influence of tidal forces. In other words, it likely originated in a debris disk, or even, more excitingly, might be a fragment of a shattered super-Earth. The modeling showed that Oumuamua-like objects can be produced through tidal fragmentation during close encounters with their parent bodies with the host stars, and then they get flung out into interstellar space, said Professor Emeritus of Astronomy and Astrophysics at Santa Cruz, who participated in the study. So, rocky rather than icy interstellar bodies might be more common than we think. Researchers anticipate more interstellar visitors with similar traits will be observed when the Vera Rubin Observatory comes online. And a friendly reminder, NASA has been celebrating the 50th anniversary of successful failure Apollo 13 all week long. That's been fun, but just want to mention that their command module pilot, Jack Swigert, got to file his taxes before he went into space. The mission blasted off, and he had to file an extension for being, well, out of the country. Many of us do have very good reasons for filing a tax extension this year, but we just wanted to remind you, even an astronaut can't always be on the ball, but we don't want to have to beg Richard Nixon's ghost for tax forgiveness, so file your taxes. In the sky, hopefully a lot of you got to see the planet show that's been going on in the early morning. Today was the last good day or in alignment with Mars, Jupiter, Saturn, and the Moon. The Moon and Mars are speeding away from the other two. We did have a nice window of clear sky this morning between 2 a.m. and 8 a.m., and Jonathan and I got to see it, and it was quite nice. Didn't get any pictures, though. But next on the agenda, the Lyrid meteor shower is on, ending the months-long drought for major meteor showers that goes from January until April. It officially starts today, the 16th. It runs through the 25th. The peak will be on the night of the 21st. Lyrids are not a particularly stored meteor shower, but a couple things in its favor. One, the moon is going to be a new moon, so you're going to have a dark sky. Two, current events have led to many industrial shutdowns and a lessening of light pollution and of particulate matter. You may have seen the photos of the Himalayas or LA with crystal clear blue skies. Upshot is, this might be a surprisingly good time to take in a meteor shower from your own backyard. The Lyrids are produced by debris left by the orbit of Comet Thatcher. They only really normally produce 10 to 15 meteors at peak, but have generated outbursts in the past, including some recorded by the ancient Chinese. So give it a try. It could be fun. And less happy news. Comet Atlas is not going to be the comet of the century, the much hyped comet, and we are kicking ourselves for giving into that hype, but hey, it's been a rough year and we really wanted a comet. Atlas has suffered a breakup. It has dropped already a full level down in brightness to magnitude 8.5. It is still there. It is still observable. I know some of you are observing it with your own gear, but it will not be blazing through the May skies as predicted, as we have hoped. It certainly won't be as bright as 5 Jupiters or a full moon or any of that. No worries. We have another comet to hype. Comet F8 Swan was announced this past weekend. It's currently a southern hemisphere object, but it is headed northward. It will actually be doing a rendezvous optically, not in actual space, with Atlas in next month. Swan is exciting because it's on an orbit that takes 10,000 years to complete, meaning this might be its first pass through the inner solar system, and it might do something unpredictable as it feels the heat of the sun for the first time. Or it could be like Comet Kohoutek and be a big legendary dud. But anyway, Comet Swan, check it out. Again, Southern Hemisphere object right now. It's going to be coming around next month. Keep your comet tracker on, and let's have your fingers crossed that we get a decent comet to brighten up the sky. And that is in the sky for this week. All right, so presidential report, I think I already covered it. Thank you all for continuing to participate and make the Warren Astronomical Society a part of your life while we are unable to meet one another personally. I'm very proud of how the club has kept going, all the more so since many other clubs have not been able to do these kind of remote presentations, remote open houses, and stay safe. All of you are valuable, and it's great to see you all. In the meantime, Dale Parton is our presentation chairman. Please contact him if you've got a long or short talk that you'd like to deliver, or if you are interested in being our In the News volunteer. We do have a full slate for most of the rest of the year. We have a few people whose topics are not decided, but we've got tonight we've got Cosmic Fireworks from Dr. Jerry Dunifer. We have on the 4th of May, Ken Burton will tell us about an odd couple of astronomers, Vicky and Bade. Jonathan Cade will do a brief talk on observing the local group. And then we are going to give you virtual Dave Bailey on the 21st of May to let us know the bad news if our sun were a red dwarf star. So that should be a fun and vaguely terrifying presentation. Next up, we've got Riyadh, who's our second VP / observatory chairman. Riyadh has been keeping an eye on the observatory to make sure everything is good, has been in contact with the metro parks over some things that we wanted to do up there. Of course, nobody can join him or any of us for observing, but in the event that you wish to do observations at Stargate, as members, you still do have privileges. The metro parks are open. The metro parks are encouraging people. And so please contact the board or Riyadh specifically if you are interested in going out and making use of the Stargate facilities. Okay. Treasury report. I don't see Mark Jacobson with us tonight, but the Treasury report is in the WASP. We've got Secretary report. Glenn Wilkins is turning in his bang up minutes, so they are also in the WASP. Outreach. All in-person activities in sidewalk astronomy are canceled for the duration, and we do not at this time have any plans for Astronomy Day, which is on May 2nd. In the event that we're able to get something virtual and safe lined up, it will be advertised on Meetup and MailChimp, so please stay tuned. And then publications, the WASP is out. The WASP has been coming out on time. If you have anything that you would like in the WASP, please email publications@warrenastro.org, and Jonathan, our newsletter editor, Dale Teamy, will be happy to get it there. Any comments or questions on the officer reports? Okay, special interest groups. Solar report, got it from Marty Coons last night. Nothing really happening on the sun. Hands-on, Riyadh runs that, currently on hiatus. History group. Latest adventures are chronicled in the WASP. Astrophotography, we've got Chairman Bill Beers tonight, and Bill has a brief presentation he wants to share with us, so I'd like to turn the audio over to him for a moment.
Hear me? Can you hear me?
Yes, I can.
Jonathan, how many YouTubers do we have on tonight? I can't hear Jonathan.
Sorry. Sorry. We have 24 on YouTube right now and 19 on the WebEx.
Okay, good. Good crowd. Yeah, my name is Bill Beers, and I love astrophotography. And I've been taking a lot of questions. People have been emailing me. And one of the most frequent questions I get, I'm going to try to share. I'm going to share my thing here, share my content. Share file.
Okay. Bill, I'm afraid nobody can actually hear you. I think we'll need to move on to the next report. Maybe if we can get the audio working, we can get this in during the informal discussion section of the meeting. For GLAC, GLAC met on last Friday, and GLAC, of course, is working not with the metro parks these days, but with the DNR. The DNR is not remotely ready to declare public events open for clearance. There will be a go, no-go decision on astronomy at the beach in August. And honestly, from the sound of things, the DNR wants a vaccine for COVID-19 before they proceed with any non-social distancing event. So there is still a chance that we can have an astronomy at the beach this year, but it's going to depend on a lot of factors. So we will keep you informed of what's going on with GLAC and astronomy at the beach. Oh, club logo merchandise, still available for sale. Maybe we ought to have an online catalog, Jonathan, for fundanas. And discussion group is again on hiatus.
You just want to get it out of the house.
Yes, I do.
Am I discussion group is
yes.
Yes, you are,
Bill. Why don't we try that again?
So how much of that did you not see?
We heard none of it.
Okay, I'm going to try to share my content again. Here I'm talking and nobody's listening. All right, share screen. Can you still hear me?
Yes.
Yes.
All right, let's try this again here. Can you see the screen here and my mouse moving?
Yes. Yep,
All right.
everything's good now.
Perfect. All right. One of the most frequent questions I've been getting through email is how can people use their iPhones to take pictures through their telescopes or binoculars? And a while back, Joe Tocco did a review of this little device, and I think last week Jonathan actually used this to take some pictures of some items through his telescope. So this is a handy-dandy little device from Celestron where you mount your iPhone in the bracket. You mount it to your eyepiece through around here, and this allows you to move your iPhone to line it up in 3 axes, left to right, up and down, and in and out. So what you do, you mount your iPhone on this up against your eyepiece, you hit your camera, obviously, then you focus on the object. It's best to start on the moon because it's the biggest and easiest one to start with. Focus it in, and you should be ready to go. Now, Jonathan, you've actually used this. If you have any other suggestions, feel free to chime in on the use of it.
It's really amazingly. Ooh, getting echo. It's really versatile. It works with. I actually was even able to use it with binoculars to take pictures of birds, and like dimmer. I was just really amazed that it was able to do the whole Sword of Orion really well. It was able to capture the Orion Nebula to a certain degree, and I was just using a professional photography app, but I wasn't doing any kind of time exposure or anything. If I can figure out how to do time exposure on my iPhone, I might really be able to take some impressive photos. So I just have been like, the build quality is super high. Everything is really smooth, and I can't recommend it enough for the price. Like, it's really, I can't wait till the next lunar eclipse when people are asking me to take pictures with the telescope. It'll go a lot faster this time, I think, and my hands won't freeze quite so much.
Okay, good. I have some pictures to share here also. A lot of people have been asking also where I do my imaging. So this is my observatory. Can you still hear me, John? Okay, good. This is my observatory up in Cadillac. It's an 8-foot dome. And this is what I have on the inside of it that I use to image with. What this is, 11-inch Celestron Edge HD on a Celestron mount. And here's the camera I use. It is a ZWO-071 one-shot color camera attached to the back. And all this is hooked to a laptop over here on the side where I can actually see when I'm imaging. You've all seen Doug's operation. So it's very similar to that, works on the same principle. But this is what I image through. And I have another refractor telescope that I use also, 102 millimeter that I put on the mount also. So that's what I use. And I was up there a couple of weeks ago, and we were talking about the comet. So I was able to image the Comet Atlas. Now, this is when it was still nice and bright. And I imagine Doug is probably going to show some latest images of how it looks now when it's breaking up. So am I still on, Diane?
Yes.
Okay, good. Yep. And then also at the same time, I did an image of Messier 3 the same night. This is the globular cluster. We had quite a bright moon, so I wasn't able to capture a lot of these outlying stars here very good. But for those people that don't know what Messier 3 is, this is a globular cluster, and it's 34,000 light years away from us in the constellation Canis Venatici. So it's a pretty nice bright object. So if you get a chance to observe it through your telescope, it'd be a nice object in some dark skies. It's not too far from the star Arcturus, so it shouldn't be too hard to find. Scientists predict that this cluster has got about 500,000 stars in it, so it's pretty good size. So then, other than that, I'm going to go back and how do I unshare here? Unshare. Stop sharing. Okay.
There you go.
There we are. All right, perfect. So again, if anybody has any questions about astrophotography or wants to get into it, is this right
Yeah,
side
no,
up
you
or
got it right the first time.
this way?
Move it over a little.
So this is not backwards, Diane?
This is fine. I can see it just fine.
Okay, see, it's backwards to me. Anyway, send me an email. Any questions about astrophotography? We can talk about it. I can call you on the phone or whatever, but you don't need a lot of fancy equipment like I just showed you to do some simple photography. You can use your DSLR, your iPhone, and it's a good way to start out. So that's all I have right now. Thanks.
All right. Thank you, Bill. And that is indeed a great little gadget that Jonathan uses. Okay. I think that concludes our special interest group reports. It is 8 o'clock. We have time for observing reports and asking an astronomy question. So we'll unmute so that people can ask questions or share observing reports. I know some of you have some things that you've seen in the last couple weeks.
I do, actually.
Yes.
Hello.
Hello, Riyadh. Go for it.
Conjunction of the Pleiades and Venus the other night. 2 or 3
Yeah,
nights.
that conjunction was good. What'd you see, Riyadh?
Oh, actually, that was not me. That was somebody else talking. I'm not sure who it was now.
That was me.
Bill, I
that was
think. No, not
Shedlowski.
Bill. Oh, yeah, Jim.
Or I just observed it. It was a cool thing to look at through binoculars, and it was kind of interesting to track Venus for the three nights that I looked at it as it passed by the Pleiades.
Yeah, that was beautiful, and thankfully we had nice clear skies for that. Did anybody see the planetary conjunction this week?
I saw it, but I saw it in the pre-dawn sky, and it had already gotten a little bit brighter than
Dawn comes at a bad time of
I would have
day.
liked. Yeah, these early morning conjunctions.
So I have one quick comment to make, one observation, which is actually kind of indirect observation.
Sure.
So there are a few people in the club who are also ham radio operators, like myself. Lately, I've been listening to different bands. You're usually the 10-meter band. That's the wavelength of the band, and same thing with 15 meter and 50 meter are usually active only when we have a lot of sunspots activities. But for some reason, and I only caught maybe one of the bands, the 15 meter, but some people were reporting a lot of activities on the 10 meter band. That would have been 2 and 3 days ago. So I don't know whether there's something going on in the sun that's changing the ionization layer like it normally does when there are sunspots. But something has happened, and it's this is what's going on right now. So maybe we need to, if you have a chance, if somebody's got a telescope that with filters that they can look at the sun, maybe keep an eye on that and see if we end up seeing maybe some sunspot. But something definitely is happening. Today it wasn't so good, but keep an eye on it.
That is really interesting, Riyadh. Thank you. Any other observing reports?
I've got a couple. This is Doug.
Sure thing, Doug.
Yeah,
Go for it.
I want to share a picture here. Let's see here. here. Bring this up. Okay, you see that? Maybe not. Maybe it's here. There we go. So we talked about the Venus Pleiades conjunction. I got two shots, one from the April 2nd and then one from April 3rd. So that was the one thing I wanted to share. And
What's the little, Doug, what's the artifact up there on this?
Yeah, those on both of them, there's lens flaring, and the artifact on the left-hand one is more pronounced because the Venus is so far to the lower left that flares up to the upper right. There's a flare actually on the right-hand one there, but that's because Venus is a little more central located.
So that's not a weird-looking comet, then?
No, it's just this 300 millimeter zoom lens that I have on my Canon DSLR. It's a T3i, and I have it piggybacked on the 10-inch in the observatory, so I can run both the 10-inch imaging and also through the Canon. I can put anywhere from 10 millimeter all the way out to 300 millimeter lens on it and take some things. So this was just an attempt at capturing Venus and the Pleiades there with that. Then the other thing I was going to pop in here is the latest Atlas shot. And that was taken 2 nights ago. What has happened with Atlas is it is broken up, and the actual components that are broken up are trailing the primary part. So the core looks extended in this, and there's quite a bit of more tail now. But the core is got several fragments. You can't resolve them in here, other than you can see that there's a little bit of modeling following the primary core. So this was 61-minute shots stacked on the core. So that's what I've got for today's report. Okay. Any questions on that?
Cool, Doug.
Hey, Doug,
Yeah.
I have one.
by any chance, do you have a comparison shot that you took from, say, a couple of weeks ago
Yeah, I sure do. 1 second
to
here.
compare the two differences? Because the reason I ask is Gary Ross, who's probably on tonight, he went out looking for the comet last night and he didn't have any luck. So I'm assuming it is broken up to the point beyond visual recollection.
Well, it's never been naked eye, but it is almost ninth magnitude now. Here's a
No, he was using a good sized telescope, 17-inch from what I understand.
Yeah, so this is a series of them taken through March and into the end of March. So early on in March, the left-hand one, and then these were on various days throughout the. And as you can see, the right-hand one is the brightest. That was March 21st. And then I have another one here, I think, from just a few days after. Let me check something real quick here. Yeah. Then I have one from April 5th here, which is April 5th was just before it started breaking up. That's this one right here. So this one was taken just before it broke up, which would have been 11 days ago. Okay. Anything else?
Okay.
Is it a real Kahootek? Is that what it is?
No, more like Comet Ison Part 2.
Yeah.
It was looking promising and then it disintegrated.
Yeah, that's too bad. That'll be a good one. Tough luck.
Yeah,
Indeed.
for me to remember Kohoutek, which was 47 years ago,
God, I feel old. God,
for me, it was, I had an 8-inch scope at the time when I was doing my visual observations of it for about 6 months. And I don't know if I can even compare the two because that's a long time ago.
well, it was supposed to be a superstar like this one, and there you go.
but I followed it for 6 months while everybody else just went on their way.
Yeah. No. Tough luck. What are you going to do?
I actually took another an AVO cluster 2 nights ago as well before the snow hit my observatory. But I actually posted that on the Boone Hill site. You guys can look at there.
How many failures can we have? No Beetlejuice explosion. No Katuka.
I know.
Well, the comet exploded. What do you want to explode? The comet exploded.
Yeah, the thing we didn't want to explode exploded. That's a good one.
It's all big tease, Ken.
Yeah, I know.
I don't really want Beetlejuice to explode. So we
our main speaker is going to be talking about cosmic fireworks.
Yeah.
Oh, cool. Okay.
So I have an observing report from Gary Ross
there we go.
on YouTube, and he confirms he was using a 5-centimeter refractor to look for the comet.
Oh, okay.
So that's more of a challenging recovery.
Yeah.
I couldn't see it before it broke up with my 10-inch from Dearborn, but that's from Dearborn. So
isn't it kind of terrible that Galileo had a larger telescope than Gary does?
only marginally.
Sorry.
We have a question on the YouTube. How far is the comet from the sun?
70 million miles at closest, I guess.
And is it, what population of comet is it from? Is it a periodic comet, or is it an Oort cloud comet, or what?
Apparently not a periodic.
I can answer how far it is from the Earth right about now. We're looking at about 75 million miles.
That's what I said.
75 million miles.
But they want to know how far from the sun it is.
Well, just like what its orbit is around the sun.
It's got a near parabolic orbit, so I think it's any kind of.
Astronomy magazine says it's going to hit perihelion on May 31st, and it'll be 70 million miles away from the sun. That's what Eicher said.
Right now, the sun distance, according to the SkyX, is 1.13. No, wait a minute here. 1.17 AUs.
Okay. Cool.
All right. While we were giving the special interest group reports, it looks like Marty relayed to Jonathan in text that even though there has been no sunspot activity, there has been a prominence. So if you've got a hydrogen alpha, give it a whirl. Okay, we have a couple of minutes where we can answer more questions if questions are coming. Otherwise, we can declare an informal break. We invite you to enjoy snack time and your favorite beverage in the safety of your own home, and we will reconvene at 8:30 for the future presentation.
I have a question.
All right.
Have any of you seen the recent swarm of SpaceX constellation satellites? I have a message from a number of my friends back in Arizona who essentially saw 50 or 60 of them yesterday.
Oh, wow.
Has anybody here noticed those?
I can tell you, Jim, doing imaging a week and a half ago, I did not notice an increase of satellite trails through my images at all. So I don't know if they've done something reduce the reflection of some of them, but I haven't noticed. I don't know. How about you, Doug, in your imaging?
Yeah, on any given night I get nowadays. On any given night I get approximately 2 through my images while I'm running all night long. So 2 satellites, but I don't know if that's more or less than what I normally get.
Well, apparently these are transient events. They come across in swarms, last maybe 5 or 10 minutes and that's it. So I just wondered, and they happen just before and dawn and just before just after sunset.
Right.
Just wondered if any of you had picked up those things.
Not me.
No, I would say that I haven't seen any stream of those at all.
They
But-
have been on the record as causing UFO sightings in Colorado, or rather, a rash of UFO sightings in Colorado have been traced back to the Starlink. So it depends on where you are in the country.
Prominence on the right side of the sun. That's the only one that's there. This is Soho.
That's
Yeah.
nice.
Hey, Doug. Can you, let's say, enlarge the core a little bit to see if you can see it breaking up or not? Or does that require way too much power?
Oh, can't hear you, Doug. No.
Now we can.
Yep, now we can, yeah.
So I've got to bring up the I'll bring up that one from 2 nights ago, and we can take a look at it. But I don't think I can enhance this much to. We can zoom in on it here.
I will tell you, if you're talking to yourself, Doug, you just have to not answer. That's all. And then otherwise you're.
I need to share. Let's share this right here. You guys see that?
Yep.
Yes.
Okay.
Crystal clear.
So this is the stacked one. I may be able to determine something if I just look at an individual one. But if I look at this closely, there's like a separation off the core there,
Yep.
just north of it. There's a little bit darker, and then there's a little bit brighter. I think
Yep.
that's the 2 main elements right there.
Mm-hmm.
Would you agree with that, Riyadh?
It's hard to tell, but definitely is a possibility. I do see what you're talking about. Yeah.
Yeah, looks like there's a little gradient change right here in my cursor. That would be, where the separation from the first and second component are. But what I did notice is this tail's gotten really long, but there's still quite a bit of light downstream from the core. That would be the other fragments. That's the best I could do.
Yeah, I mean, tonight should look,
What's that?
it should look a little different. It should look a little different tonight, right? Especially if it's breaking up still.
Yeah, and I'll image it tonight. Yeah, my goal in these few hours that I get each clear night is just to go after this comet for now. I tried to go after the Abel cluster 2 nights ago, and it clouded up sometime after 1:15. It did a meridian flip. It tried for an hour and a half. It got one more image, and then it parked itself because it was cloudy. And then I got up at 4:30, and went out to the observatory, and there was snow everywhere in the building. So I was a little disappointed with that, but that's okay.
Is this at prime focus?
Yeah, this is prime focus.
And it's a 10-inch f8?
Yes. I did clip a little bit off the sides. So it's a little more, it looks a little more magnified than the raw data, but it's pretty close. The other thing is the Abel cluster it went after was kind of interesting. Where is it here? There it is. This is the Abel cluster I went after last night, or 2 nights ago. Look at all those galaxies.
Whoa! Look at that.
This is called
Cool.
Abel 1656, or the Coma cluster.
So look at that.
And
Is
the
that
actual, pardon me?
Is that part of our big group? Is that a Virgo cluster?
Yeah.
It is.
And
Okay.
here's the actual image I took, and this was only an hour
All right.
because
Oh.
the clouds came in, and this is where it's solved.
So these galaxies are relatively close, actually. They're in the Virgo supercluster, right?
Well, not all of them. There's the brighter ones, yes, but some of these are out. These really dim ones are out a couple hundred million light years. The close ones are probably in the 50 million light years.
It's referred to in both maps as both the Virgo supercluster and the Laniakea, whatever it is. Supercluster.
I think
That's a good point, Jim, but it is now 8:31, so we'll need to reconvene the meeting officially so that we can have our featured presentation tonight. And as ever, I would like to turn things over to our program chair, Dale Parton, for the introduction.
Okay. Well, our speaker for tonight is well known to the club, Dr. Jerry Dunifer. He is a physics professor emeritus at Wayne State University. Been on the faculty there for 35 years, including the associate chairman of the department for quite a long time. He's also been active in the astronomy programs of the department, including the planetarium. And we've heard a number of his presentations in the past of visiting observatories all over the world. He's been all the way from the South Pole to the North Pole. He probably qualifies as the most traveled person in the club. I'm quite interested to hear his presentation tonight, Cosmic Fireworks. Jerry, take it away.
Okay, thank you, Dale. And hello to everybody out there in cyberspace. Let me see if I can get this set up properly. Okay, is everybody getting my first slide, Cosmic Fireworks?
It's looking good.
Okay, very good. So, about 67 years ago, when I was in the 7th grade, I became very interested in the field of chemistry, in particular, the chemistry of explosives. So I bought myself the largest Gilbert chemistry set available and supplemented it with all the additional chemicals that the local drugstores would sell me. Then I began experimenting in my enclosed back porch. So pretty soon I was generating small bangs and pops, clouds of smoke, and very noticeable stenches. And as you might guess, my mother and father were not pleased. So my father, who had considerable carpentry skills, went to the furthest corner of our property and he built a small shed which became my laboratory. So out there in my lab, I spent many happy hours in my experimental study of pyrotechnics. I developed a number of devices, homemade fireworks, firecrackers, rockets, small and medium-sized bombs, cannons, depth charges, and so forth. I still have all my fingers. I was lucky in that my neighbors were very understanding, and even the local police. And when I look back now, I'm amazed that I was able to get away with so much. Since that time, I've maintained my interest in devices and events which can release a large amount of energy in a short period of time, which gets me to tonight's topic, cosmic fireworks. I'd like to take a look at a few examples of events in the universe which can be described as explosive events. I'm going to be considering 5 types of events: solar flares, novae, novas, kilonovae, supernovae, and quasars. And these are in order from smaller scale to larger scale events from top to bottom. I'm going to begin with solar flares that you see in the picture here. And I've listed here some of the characteristics of these solar flares. Often occur on the sun's surface as eruptions or explosive events, which are found either in sunspots or sunspot groups. And they are associated with magnetic fields around the sunspots. In particular, they arise when there are sudden changes occurring in the magnetic field pattern. They are sometimes associated with solar flares known as coronal mass ejections, in which hot plasma is ejected with high speed out into space. Flares generally last from a few minutes up to tens of minutes. And I saw one several years ago looking at the sun through an H-alpha filter, and the one that I saw lasted for about 15 minutes. The kinetic energy of a 2-kilogram object moving at 1 meter per second is 1 joule, and that is the standard unit of energy in physics. Largest flares on the sun may release up to 10 to the 25th power of joules, which is 10 trillion times a trillion joules. The most energetic flares release 50 million times more energy than the largest hydrogen bomb that has been tested on Earth. The estimated energy in the world's fossil fuel reserves, that includes coal, gas, oil, is something like 4 times 10 to the 22nd joules, which is 250 times less than the energy in the largest solar flare. Electromagnetic waves and particles released by a solar flare may hit the Earth, in which case they can have a variety of effects, such as generating geomagnetic storms, disrupting radio communication, producing intense aurora, and they can also constitute a hazard to astronauts who may be in space at the time. The largest documented solar storm in the last 500 years to hit the Earth with a coronal mass ejection is known as the Carrington event, which occurred September 1st, 1859. Named after Richard Carrington, who was an English astronomer who was among the first to observe and report the solar eruption. This particular event generated auroras which were seen down to south central Mexico, and it fried parts of the telegraph systems in the US and in Europe, as well as giving shocks to telegraph operators. An event like this today, it is estimated, would do more than $1 trillion in damage. I have here a few examples of solar flares. So this is a solar flare which is happening right here on the sun. This particular one occurred on September 6, 2017. And here's an example of a coronal mass ejection, which is occurring at the same month in the same period of activity on the sun. For example, of a solar flare. And this is an example which was recorded on June 7th, 2011 in the extreme ultraviolet by a NASA satellite, the Solar Dynamics Observer. This is a false color representation, obviously. since the photograph was in deep UV. Now we get to the mathematical part of this talk, which everybody's looking forward to. Well, these are Maxwell's equations, these four equations that you see here at the top. In these equations, E represents the electric field. This can exert forces on the electrically charged particles. And B represents the magnetic field. Exert forces on moving electrically charged particles. So the equations tell us how the electric field and the magnetic fields are interrelated. And let me take a quick look at the third equation here. This equation. This is now in the language of vector calculus. It tells us that the curl of the electric field at a given point in space is given by minus the derivative with respect to time of the magnetic field. That is, an electric field can be generated by a changing magnetic field. Since these flares occur in the vicinity of magnetic fields around sunspots, and in particular fields which may be changing relatively fast, these changing magnetic fields produce electric fields, and since the sun's plasma is made up of charged particles, these can be accelerated by the electric field and give rise to solar flares. So that's my math lesson for the day. So now moving on to the second category, that of novas, or novae, or novae. We have displayed here an example. This is the remnant of a supernova explosion, which occurred about, a nova explosion, which occurred about 120 years ago. I'll be saying more about that in a few more slides. I've listed here some of the characteristics of novae. These are explosions which take place on the surfaces of white dwarf stars. Furthermore, these white dwarfs are orbiting with a nearby second star, which is often a red giant star, which may have a diameter of 100, even 1,000 times the diameter of our own sun. Two stars in the binary system are sufficiently close together that plasma, ionized gases consisting mostly of hydrogen, is pulled from the surface of the larger star down to the surface of the white dwarf. The hydrogen accumulates in the surface layer on the white dwarf until sufficient temperatures and pressures develop within that layer that a thermonuclear explosion is triggered. And this is the nova event. Since the nova event depends on the characteristic of white dwarf stars, I've given some additional information here about the characteristics of these. White dwarfs are small, compact stars, which typically might have about the same mass as our sun, but are only about the size of the Earth. Such stars would have an astonishingly high density. These are stars in which all the nuclear reactions have finished. One day, our sun is going to become a white dwarf, after all the hydrogen in its core has been consumed. White dwarfs are supported by electron degeneracy pressure. This is a requirement of the laws of quantum mechanics. Because of the type of particle that the electron is, class of particles called fermions, electrons obey the Pauli exclusion principle, which is well known in chemistry, which states that no two fermions, or in this case, no two electrons, can occupy the same energy state. This forces most of the electrons in a white dwarf star to be at very high energies, often moving at speeds close to the speed of light. This large kinetic energy of the electrons provides sufficient pressure to support the star against further gravitational contraction forever. No matter what the temperature of the star, no matter how long it takes to cool off, it will always be supported by this electron degeneracy pressure. The typical density of matter in a white dwarf is about 1 million grams per cubic centimeter. That's 1 million times the density of water. Now, one unusual property of a white dwarf is that the more mass in the white dwarf, the smaller its size. If you start with a given white dwarf and add more mass, larger mass will increase gravity at the surface of the star. This will cause the star to shrink in size. And this will push the electrons inside to higher energy states, which will provide the additional pressure needed to support that smaller star. And finally, it turns out that there's a maximum mass that a white dwarf can have. Maximum mass is about 1.44 times the mass of our sun. At this mass, the white dwarf size shrinks to zero. This maximum mass is known as the Chandrasekhar limit. Here is a picture of the professor. Subramanian Chandrasekhar was professor of astrophysics at the Yerkes Observatory and the University of California. He was an American astrophysicist of Indian origin. He received the Nobel Prize in Physics in 1893 for his work, The Structure and the Evolution of Stars, which included his original work on white dwarfs, taking into account the effects of special relativity. A few years before his death in 1955, he came to give us a talk at Wayne State University. More about the properties of a white dwarf. Here we have the Earth, size of the Earth, compared to the size of a white dwarf of 1 solar mass. And it turns out for this mass, the star has a diameter which is about 90% the diameter of the Earth. Gravity is so strong at the surface of the white dwarf that the escape velocity is approximately 2% the speed of light. To illustrate how dense the material is, if one could go to a white dwarf, scoop up 1 teaspoonful of material from the white dwarf, bring it back to Earth and weigh it, it would weigh approximately 5 tons. 5 tons per teaspoonful. This is a graph of the characteristics of a white dwarf, plotting its radius as a function of its mass. So on the horizontal scale, the increments are in 1/4 solar masses, and plotted vertically is the radius of the white dwarf in terms of the sun's radius. So what you see here are 2 curves. There's an upper one which is blue in color, a lower one which is green in color. The upper one is calculated using classical mechanics. That is Newton's laws of motion, like F equals ma. The bottom curve is calculated using Einstein's special theory of relativity. And that, in fact, is the correct theory. And that is, in fact, the theoretical calculation that was first done by Chandrasekhar. What you can see in these plots is that for small mass, when we're down in this vicinity, 2 curves are essentially the same. But as we move towards higher mass, they break away from each other. That is, the relativistic curve indicates a smaller radius, and the reason they separate from each other is because the electrons within the white dwarf, we go to higher masses, are approaching speeds getting closer and closer to the speed of light. And as I indicated, there is an upper mass. That mass is the Chandrasekhar limit. Here it's called the ultra-relativistic limit, which is 1.44 solar masses. And the Fermi gas, which is referred to for both curves, is simply referring to the electrons within the white dwarf. Oh, here's a photograph of a real white dwarf, which is the smaller star with the arrow pointing towards it. The name of this star is Sirius B. This is the nearest white dwarf to Earth. As most of you know, Sirius is the brightest star in the sky, and it is actually a binary star system, Sirius A and Sirius B. Sirius A is a much brighter one. They orbit each other about every 50 years, being separated from each other from 8 to 32 astronomical units, with the orbit being quite elliptical. Distance from Earth is 8.6 light years, which is twice the distance to Alpha Centauri, our nearest star system, which is 4.3 light years away. Sirius B was discovered in 1862 by Alvin Clark, an American telescope maker, using an 18.5-inch refractor, which is now located at the Dearborn Observatory on the campus of Northwestern University, just north of Chicago. If you're ever in the Chicago area and would like to visit something interesting, then can go up to campus and see that telescope. Sirius B is 10,000 times less luminous than Sirius A, even though its surface temperature is much hotter, about 25,000 Kelvin. Now, I've actually seen Sirius B while looking through an eyepiece of an 18-inch telescope on one of my trips down to Chile. I'm wondering how many other members of the club perhaps have seen it as well, looking through an eyepiece of a telescope. So this next slide, I show the geometry which can lead to a nova explosion. So we have a sun-like star on the left with matter streaming through space and going into an accretion disk around a white dwarf, which is on the right side. This material swirls around and is ultimately deposited on the surface of the white dwarf, where once sufficient temperatures and pressures are reached, nuclear fusion reaction occurs, converting hydrogen into helium, taking place on a good fraction of the surface of the white dwarf star. This is the nova explosion. Another artist's visualization of what is happening with the white dwarf on the right, stream of gas, and a sun-like star. That sun-like star could also be a much larger star, like a red giant. Oh, here's a photograph of an actual nova near its maximum brightness. This is Nova Eridani, 2009, which exploded in November of 2009 and reached a maximum brightness corresponding to an apparent magnitude of 8.4, which is a little bit too faint to be seen by the naked eye. Distance of this nova from Earth is about 12,000 light years. This particular photograph is a 2-minute exposure using a 14-inch telescope. Also shown here is the magnitude of 3 other stars in the vicinity. The star with a magnitude of 15.4 is about the same brightness as Pluto, if it were to appear in the photograph. This is a photograph you've seen a little bit earlier. This is sometimes known as the Firework Nebula. This is the remnant of Nova Persei, 1901, also known as GK Persei. On February 1901, it reached a maximum brightness with an apparent magnitude of about 0.2, which is similar to that of some of the brightest stars in our sky. The event took place 1,500 light years distance from Earth. Nebula has a diameter today of about 0.7 of a light year and is expanding at about 1,200 kilometers per second. This is another view of that same nova remnant. This particular one is a false color composite photo, combining observations made at 3 different wavelengths: X-rays, visible light, and radio waves. So in blue is the observation made in the X-rays using the Chandra X-ray Observatory in orbit. And yellow is the visible light observation using the Hubble Space Telescope. And in pink are radio waves using the VLA, Very Large Array in New Mexico. Oh, going on to the next category, our third category, the kilonova. Kilonova is an event which puts out approximately 1,000 times more energy than a typical nova. And our most recent, or one of our most recent observations of such a type of event was the collision of two neutron stars with each other, as shown in this artist's depiction. So this most recent observation took place first as a gravitational wave detection, known as GW 170817. It was seen as a gravitational wave that was detected by LIGO in the US and Virgo in Italy, and it was observed on the 17th of August 2017. Collision was also seen across the electromagnetic spectrum by 50 observatories on Earth and by a number of satellites in orbit around the Earth, including the Fermi Gamma Ray Space Telescope, which detected a 2-second burst of gamma rays coming from this event. The event occurred in an elliptical galaxy 140 million light years from Earth. Since the event involves neutron stars, I've listed here some of the characteristics of a typical neutron star. These are incredibly small stars with a diameter of perhaps 10 miles and a mass most likely in the range of 1.4 to 2 solar masses. At the very most, they cannot have a mass in excess of 3 solar masses, which is required by the laws of general relativity. As you might guess, they are composed mostly of neutrons. They have enormous density, horrendously enormous density, 10 to the 15th grams per cubic centimeter, the same as the density of an atomic nucleus. Turns out that neutrons have the same classifications as electrons in that they are fermions, and they therefore obey a Pauli exclusion principle. In the same way that electrons can support a white dwarf star, neutrons can support a neutron star through neutron degeneracy pressure. It's through a combination of neutron degeneracy pressure and direct neutron repulsion in the star that the neutron star is supported and prevented from the ultimate collapse into a black hole. Neutron stars may have rapid rotation on their axes and intense magnetic field. Stars are often seen as pulsars, giving off flashes of light and other forms of electromagnetic radiation with each rotation. And it has been estimated that there may be up to 100 million neutron stars in the Milky Way galaxy. Oh, for comparison purposes, it shows a typical neutron star compared to Manhattan Island, New York City. As you would guess, this would be a very dangerous situation for New York, and be a very dangerous situation for the entire Earth, to be rapidly consumed by the intense gravity coming from the neutron star. Here's another comparison. Size of a typical neutron star compared to the city of Vancouver, British Columbia, up in Canada. Now, if we were to go to a neutron star, scoop up 1 teaspoonful of neutron star stuff, and bring it back to Earth and weigh it, it would weigh something like 10 billion tons. 10 billion tons per teaspoonful. That's about the same as the weight of a mountain on Earth. Here you have a mountain in a teaspoon. Here's an artist depiction of two neutron stars which are about to collide. They're swirling in an orbit around each other. The wave-like pattern you see represents the gravitational waves which are moving away from this orbiting pair at the speed of light, carrying away energy which allows these two neutron stars to rapidly collide with each other. Another artist representation of two colliding neutron stars. An artist's view of colliding neutron star, the event which produces a kilonova. Okay, moving up in energy, we're going to go to the supernova. Supernova is an exploding star. Release as much as 10 to the 21st power, big number, which is 1 billion times 1 trillion times the energy released by the largest solar flare coming from our sun. So here I've listed some of the characteristics of supernova. These are massive explosions which can totally destroy a star. There are two types, two general types. Type 1, which involves a binary star system containing a white dwarf and another star. And type 2, which is a massive single star which undergoes gravitational collapse in its core. The energy release can range from 10 to the 44th power up to 10 to the 46th power in joule. The visible light generated will in general decay over several months of time. And estimated that there may be 3 supernova events occurring per century in the Milky Way. Most are not seen because they are too far away with too many dust clouds in between. I've mentioned here 3 famous ones. There was a supernova recorded by Johann Kepler in 1604. This was the last supernova that was visible to the naked eye in our Milky Way galaxy. Then there was supernova 1987A, which is the most recent supernova visible to the naked eye. It was not in our galaxy. It was located in the Magellanic Cloud, the Large Magellanic Cloud, which is a satellite galaxy to the Milky Way. And then there is the Crab Nebula, which is the remnant of a supernova explosion recorded by Chinese astronomers back in the year 1054 AD. Although there are at most a few per century in our galaxy, most all of them unseen, there are several hundred per year which are detected in other galaxies. There are number searches going on continuously using robotic telescopes, constantly scanning the skies for new supernovae in distant galaxies, both by professional astronomers and by amateur astronomers. Oh, this slide illustrates a number of steps which are involved in the creation of a type 1 supernova, most common of which is a type 1A supernova. So starting here at the upper left, we have 2 normal stars in orbit around each other, binary pair. More massive star will burn its fuel faster and eventually evolve into a red giant, as you see in the next picture. Given time, the outer layers of the red giant are discarded, and what we were left with was what was the original core down at the center and becomes a white dwarf. We can now skip down to this picture, picture number 6 here. We have one of the original stars still in orbit, now in orbit around a white dwarf star. As time evolves, the normal star, which originally had less mass, will use up its hydrogen fuel down in the core and then evolve into a red giant itself. And if this is a close binary pair, material can be pulled off the surface of the red giant down onto the surface of the white dwarf star. Now, this is starting to sound probably like our description of the nova which we had earlier. However, turns out it's possible for something much more catastrophic to happen. If the white dwarf is close in mass to the Chandrasekhar limit, which is already an unstable situation, the extra mass may start a runaway process in which the white dwarf begins to collapse further, raising the internal temperature and pressure. And if these are raised high enough, it can generate a sudden and explosive thermonuclear fusion process throughout most of the volume of the white dwarf. And that's what we see in this next picture. In a few seconds, a significant fraction of the white dwarf undergoes nuclear fusion with the elements inside, such as helium, carbon, and oxygen. The star is blasted apart with the outer layers accelerating outwards with speeds of up to 3% the speed of light. The inner portions may collapse into a neutron star. Within those few seconds, about 1 to 2 times 10 to the 44th power joules of energy is released, and the exploding star will reach an absolute magnitude of about minus 19.3. This turns out to be very consistent and constant for this type of explosion. This makes type 1 supernovae standard candles, which can be used to measure large distances throughout the universe. It is through a study of type 1a supernovae, astronomers have reached the conclusion that the expansion of the universe is actually accelerating. And this is now attributed to something called dark energy. Don't know exactly what it is, that's what we call it. Artist representation of what happens just prior to type 1a supernova. Again, matter being pulled from a much larger star, streaming through space, and being deposited on the surface of a white dwarf, which is just about ready to detonate in this representation. Okay, let's look at a type 2 supernova. Might represent the interior regions of a single massive star. The star may have started out with solar masses or more. Such stars, the temperature and the pressure can reach much higher in the core than happens in our own sun. This allows the initial hydrogen, after it's converted into helium, for additional fusion to take place, in which the helium is then converted into carbon. And then later for the carbon to fuse into higher elements such as oxygen. As the star ages, the core temperature rises higher and higher, allowing heavier elements to be formed going up the periodic table of the elements, to be created all the way up to iron. What's shown in this picture is a variety of different elements, with iron here concentrated at the very center of the core. So we end up with an onion-like structure, which has concentric shells having different types of fusion taking place at different temperatures inside each shell. At the furthest out from the center, where fusion is taking place, temperatures are lowest and hydrogen is being converted into helium. Moving inwards, the temperatures are higher, sufficiently high that helium undergoes fusion and is converted into carbon. Then moving inwards, we can have carbon fusion taking place, producing heavier elements, till we get to the very center where we have an iron core. Now, through the production of iron down in the center, all the previous nuclear fusion processes have released energy which can help support the star against gravity, which is always trying to pull the star tighter together. Fusion of iron and all heavier elements, however, is very different. Instead of releasing energy to help support the star, these fusion processes absorb energy. So suddenly down in the central core, there are no longer any nuclear processes which can support the star. This can lead to the sudden, by sudden within a few seconds, gravitational collapse of the stellar core. Collapsing core may reach speeds of 25% the speed of light as matter rushes in towards the center. Gravitational potential energy is converted into kinetic energy during the collapse, and depending on the mass, the collapse may be complete down into a black hole. Or the collapsing core may form a neutron star. There are many types of reactions, nuclear reactions taking place very fast, and huge numbers of neutrinos are released over a 10-second period. So this is illustrated in the next slide here. We start out with a pre-supernova star, very massive star. Eventually, the core undergoes the type of collapse I described, and neutrinos are emitted in huge numbers. If there is a neutron star in the center, the collapsing material falling on the neutron star can be strongly repelled, bouncing outwards, producing a shock wave which goes outwards to the surface of the star, where the surface can be ripped apart, giving rise to the supernova explosion. At which point, as the size of the star expands, we see increasing light coming from the star. This is the type 2 supernova. In this type of an event, the star can brighten by 100 million times, 10 to the 8th power. During the brightest part of this explosion, light given off by this supernova can outshine all the other stars together in the galaxy in which it is located. This graph shows the light curves of supernovae as they plot the brightness, the intensity of the light as a function of time. So plotted vertically is the absolute magnitude of the star. This is a logarithmic representation of the brightness or the luminosity as a function of time. Horizontally, you're plotting time extending over almost 6 months. So there's a number of different curves here corresponding to type 1 and type 2 supernovae of several different subclasses, which I won't go into. So just to remind you, this absolute magnitude is representing the brightness on a logarithmic scale. It's at a change of 1 magnitude, represents a ratio of brightnesses for 2 stars about a factor of 2.5. And a change in luminosity of 5 corresponds to a ratio of brightnesses of a factor of 100. So absolute magnitude minus 19 is 2.5 times brighter than magnitude minus 18. Magnitude minus 19 is 100 times brighter than magnitude minus 14. So the brightest curve that you see here is for the black curve, and that is for type 1A supernova. So you might think this gives off the most energy, because if you look at the type 2 supernovae in the curve, they're down about a factor of 5 or so in luminosity. However, that's not correct. Turns out that a type 2 supernova in general is much more energetic than a type 1A by about a factor of 100. What happens is that for type 1A, about 1% of the energy which is released goes into electromagnetic waves. For a type 2 supernova, only about 1/10,000 or less of the energy goes into electromagnetic waves. For a type 2 supernova, almost all the energy goes into the neutrinos, more than 99.9%. They are released, and almost none of which are detected. Okay, here's a series of photographs showing a type 1a supernova. So these are a series of pictures. This is the first one, and then we go with increasing time to the right. And then we jump down to the lower pictures and then go again from left to right, increasing in time. Supernova itself is this bright point of light just above the nucleus of this distant galaxy. This is a barred spiral galaxy, NGC 1365, 60 million light years distance from Earth. So we start out on the far left, on the upper picture, a string of pictures. This is a supernova here, and it's relatively faint. And then within just a few days, it becomes relatively bright, and is brightest on the fifth picture, which is my 14 days after the first picture was taken. And then we jump down to the lower set of pictures. We advance in time. We see it remaining bright for a while, and then it begins to fade, and is considerably fainter within the last picture. So it's at its brightest in photo number 5, 14 days after the first photo, clearly fading by November 22nd, and it's much fainter by January 15, which is, January 17, which is 64 days after the peak. It's clear from the photos that you don't need a really big telescope to record an interesting event like this. Certainly helps to have a dark sky. So this was photographed down in La Silla Observatory, where I've been a couple times, by a French astronomer, Alain Clopes. This shows a supernova remnant, which is in the upper left-hand corner. This is the remnant of supernova SN 1572, which was first recorded by Tycho Brahe in November of 1572, located in the constellation of Cassiopeia, and at its peak, it was as bright as Venus, visible during the daytime. It was visible to the naked eye for about 2 years. Close up of that same remnant, explosion occurred about 9,000 light years distance. The debris is still expanding at a speed of some thousands of miles per second. This particular photograph was taken in the infrared by NASA infrared satellite WISE, W-I-S-E. This is another supernova remnant. This is an image of Kepler's supernova remnant, supernova 1604. It was visible to the naked eye for 18 months. It was about 23,000 light years distant. And this particular picture is a composite image consisting of X-ray, visible, and infrared components. So the blue in the picture represents high-energy X-rays recorded by Chandra. Green is low-energy X-rays recorded by Chandra. Yellow is visible light recorded by the Hubble Space Telescope, and red represents the infrared recorded by the Spitzer Space Telescope. Shows you nearest maximum brightness, supernova 1987A. This is star-like feature you see here, located in the Large Magellanic Cloud at a distance of 168,000 light years from Earth. And in case you're curious, Up a little bit and over to the left, this is the famous Tarantula Nebula, which is also located in the Large Magellanic Cloud. So this supernova event occurred on February 23rd, 1987, reached an apparent magnitude of +3. So it was easily visible to the naked eye, at least if you live far enough to the south. This was a type 2 core collapse supernova. Astronomers have been looking for years to see whether or not they can detect the presence of a neutron star, a pulsar in the center of the debris field. There is a report that came out in late 2019 that at long last ALMA, radio telescope array in Chile, may have detected a neutron star behind a cloud of dust in this expanding debris cloud. I have not seen any confirmation of that report so far. I would be interested if, in fact, there is. So there was a burst of neutrinos, which was detected on Earth from this event some 2 to 3 hours prior to the increase in visible light coming from the star. There was a horrendous number of neutrinos that were generated during the core collapse, some 10 to the 58th power, of which 25 were detected on Earth. These neutrinos came in a burst lasting 13 seconds, and they were detected at 3 sites. 8 neutrinos detected in the USA at the IMB, which is the Irvine, Michigan Brookhaven detector, which was in the Morton Salt Mine, 600 meters underground on the southern shore of Lake Erie, near Fairport Harbor, Ohio, about 150 miles from here. In Japan, they detected 12 neutrinos with the Kamiokande 2 detector, and in Russia, they detected 5 neutrinos in the Baksan Neutrino Observatory. Two photos that were taken about 20 years after the supernova explosion. The one on the left is in the X-ray band, taken by Chandra, and the other one on the right is in visible light using the Hubble Space Telescope. The ring that you see is the interaction of a supersonic shock wave expanding from the supernova explosion, reaching a ring of material that was ejected from the star about 20,000 years prior to the supernova. You can see the ring is dense and clumpy, has a diameter of approximately 1 light year. The shock wave continues to move outward at about 1,800 kilometers per second. Oh, here is one of my favorite objects in the sky. This is the very famous Crab Nebula. Picture is taken by the Hubble Space Telescope. This is designated as M1. It is the first entry in the list by Messier of nebulous objects that are not comets. This is the remnant of a type 2 supernova, explosion witnessed and recorded in 1054 AD by Chinese astronomers. Nebula is at a distance of 6,500 light years and is still expanding. Debris is expanding at a speed of about 1,500 kilometers per second, which is about 0.5% the speed of light. Nebula that you see here is about 11 light years in diameter and an angular diameter about 7 arc minutes. And in the center of this cloud, this neutron star spinning on its axis 30 times a second, which is a famous Crab pulsar. And this gets me to my last category, the celestial fireworks, that of quasars. These are, in general, thousands of times more luminous than supernova explosions. What you see here is an entire galaxy surrounding the quasar. When I was a graduate student back in the 1960s, two big discoveries in astronomy, pulsars and quasars. Pulsars were quickly figured out in a matter of months. Quasars took decades to determine what they are. Quasar stands for quasi-stellar radial source. They're also known as quasi-stellar objects, or QSOs for short. They are in general very distant, extremely luminous nuclei of galaxies. In these galactic centers, gas from an accretion disk is falling towards a supermassive black hole, with masses ranging from millions to billions of times that of our sun. Immense gravity of these black holes can convert up to 30% of the mass of infalling material into radiated energy. Typical quasar can consume 10 solar masses per year. The most luminous one can consume 1,000 solar masses per year. Their luminosities are 1,000 of times the luminosity of our own Milky Way galaxy. They emit electromagnetic radiation over all wavelengths, from gamma rays to radio waves, and it turns out they were more common in the past, being most numerous around 10 billion years ago when the universe was 1/3 of its present age. And about 10% of them have an associated jet, relativistic jet, which has been detected. Most famous quasar is 3C 273. Object 273 in the third Cambridge catalog of radial sources. It is optically the brightest in the sky and one of the nearest at a distance of 2.4 billion light years from Earth. And its central black hole has a mass of about 900 million solar masses. This is another artist representation of a quasar, this one having two jets, relativistic particles, which are seen here. Here is a plot of the spatial density of quasars as a function of time. So we have density vertically and age, time horizontally. Time 0 corresponds to Big Bang. Time 1 at the right, whereas it represents the current time. According to the graph, the density of quasars peaked around 35 times of what it is today, and the universe was about 5 billion years old, 1/3 of its current age. Here it is. This is a photo of a quasar 3C 273, as indicated by the arrow. It has an apparent magnitude of 12.9. It's too faint to be seen by the naked eye. It can be seen in a 6-inch telescope. Because of the expansion of the universe, this particular quasar is receding from us at a speed of 15% the speed of light. This quasar has a luminosity of 4 trillion times that of our sun in the visible band. And if we were to take this quasar, move it into the Milky Way galaxy, and position it 33 light years from us, it would appear as bright in the sky as our own sun. This is another photo of 3C 273, taken by the Hubble Space Telescope's Wide Field and Planetary Camera 2. This is the first quasar to be identified. It's the brightest one in the sky. It is located at the center of a giant elliptical galaxy in the constellation Virgo. And this cloudy streak that you see here to the upper left, that is a jet measuring 200,000 light years in length, which is twice the diameter of our Milky Way galaxy. This particular quasar was discovered in the early 1960s by astronomer Alan Sandage, who worked in the Mount Palomar Observatory. And so, that brings me to the end of the talk. In summary, we have talked about solar flares, which are eruptions on the surface of the sun. We've talked about novas, thermonuclear explosions on the surface of the white dwarf stars. We've talked about kilonovas, 1,000 times bigger, an example of which is a collision of 2 neutron stars. We've talked about supernovas, which generally lead to the complete destruction of a star. And finally, we talked about quasars, which result from accretion disks feeding matter into supermassive black holes into the centers of galaxies. You might ask yourself, we've gone from smaller, bigger to still bigger explosive events. Are there still bigger explosive events which can be found in the universe? Well, I can think of at least one, and that would be the Big Bang. Okay, that concludes my talk. Thank you for your attention. And now let me see if I can get out of the mode I'm in here.
All right. Thank you, Jerry. Since there's no library that we need to vacate, I believe we have time for some questions.
I have a question.
Yes, Bill.
Jerry, excellent job, first of all. I've always wondered. Oh, can you hear me?
Sir, go
I
ahead.
can hear you, Bill. Yes, go ahead.
Jerry, I've always wondered how far away would we have to be here on Earth from a supernova that went off that would not affect us? What do you think?
Yeah, that's a good question. Let me search my across articles about that. It depends on the type of supernova, but I think in general, tens of light years is considered safe. So maybe something like 30 light years. We would certainly survive. Worry that the radiation from the supernova might affect our atmosphere. In particular, it could disrupt or destroy a good fraction of the ozone layer, which is up for some time.
Okay, good.
The ozone layer, of course, absorbs ultraviolet from the sun, and so we might have to wear a lot of sunscreen for several years following such a close event.
Okay.
I have a question, Jerry.
Yes.
I read, I believe when we were talking about the LSST telescope, that there, on the average, there's one supernova explosion in a galaxy per century. That was an average value I read about someplace.
Yes, yeah. Well, the number I gave was
3.
in our galaxy, the Milky Way, there may be 3 per century.
Yeah. Okay.
That's on average.
Thank you.
So, Jerry, we have a question from YouTube.
Yes.
How are white dwarfs used to measure distant galaxies? I think. How does the Henrietta Swan-Leavitt scale work?
It turns out that, as I mentioned, the Type 1A supernova, if they can be identified as Type 1A, in the nature of their spectra, they all reach approximately the same absolute magnitude of minus 19.3. So that tells us how much energy is being radiated into space visually. Knowing how much energy is radiated, we can then look to see how bright that supernova appears. Of course, the closer it is, the brighter it will appear. Further away it is, it will appear fainter. By doing a quantitative measurement of just how bright that supernova is and identifying it as a Type 1A, we can determine what the distance is to that supernova.
Just a comment too, the ability to do what Jerry just described is relatively recent. It only occurred in 1998, I believe it was, when they were able to calibrate those Type 1A supernova candles, or standard candles, to measure the acceleration of the expansion of the universe. The LSST and other surveys are designed. One of the big goals is to identify more of these Type 1A supernovas to get a better precision on the measurements.
Yeah, I think the proportion, like this, the the percentage expansion was known, but not the actual absolute values. Is that correct, Jerry?
Well, we're still determining what the expansion rate is today.
Fair enough. Yeah, fair enough.
Because there's some uncertainty and they keep coming up with slightly different numbers. But by looking at what it is today here, what it is further away in the universe, and what it is very far away, it appears that the rate at which this expansion has progressed with time is not that it is slowing down as you would expect due to gravity, but just the opposite. The expansion rate with time appears to be speeding up. So there is something out there which is causing this, which astronomers have labeled dark energy.
We have another comment from YouTube. Norb Vance from Eastern
Norbert?
Michigan,
Yes.
and Emery Erdelyi are also tuned in on YouTube, and they just wanted to say hi, I believe.
Oh, very good. Hello, Norbert. And who else?
Emery Erdelyi.
Oh, hello to both of you.
And then also there's a comment, how close is the nearest neutron star to the Earth, since there's a lot of them?
Well, that is a good question. We don't know the one in the Crab Nebula, 6,500 light years away. I cannot think of any. The answer is I don't know. I can tell you how far that particular one is away. I don't know what the nearest one would be. Perhaps that one, perhaps another one.
All right. Are there any other questions?
Great job there, Jerry.
All right.
Thank you.
All right, everyone. Well, thank you very much for joining us tonight. That was a great presentation. Since there is no gastronomy to do together tonight, again,
Go get
got
something.
some snacks, enjoy them. Otherwise, we hope to have a open house, virtual open house, when conditions are favorable.